Welcome back. This is lesson 5.3, which is dealing with force problem solving and examples. So in the previous lessons, we've talked about free body diagrams and how to represent forces using pictures. We've also discussed the idea of net force and specific forces, and now we're going to put it all together and solve some force problems. So here we go. So just to review the steps in solving force problems, the first thing you want to do with all the force problems that you ever encounter is draw a free body diagram. So you're going to draw the dot with the arrows pointing, labeled, pointing in the direction that their forces are pushing or pulling, labeled with whatever they are. So whether it's gravity or normal force or friction or tension or whatever force it might be, just some applied force. Then you're going to fill in a table which will organize all of those different forces from your free body diagram. So we'll stress that, and then you're going to label it with positives, negatives, and zeros. So 0 if there is no force in that direction, positive if it's acting in the positive direction, negative if it's acting in the negative direction. Then you're going to use your equations to solve for the actual values for the force. So if it's not given in the problem, you might have to use one of these force equations down here, like the net force or the gravity force or the force of friction equation. These other forces, Fx, that's for something moving in the x direction, Fy with a force acting in the y direction. This is centripetal force, which we haven't discussed yet, so don't worry about that one. So you're going to use those equations and figure out the values to put in the chart. And then it's a pretty simple process where you just add the columns together to get the net force in the x direction and the y direction. So x direction horizontal, y direction vertical. And then if you need to, you're going to use the net force is equal to ma to solve for the acceleration of the object. So that's sort of the process that we're going to use, and I'll refer back to this in the examples we're about to do. Also, just to clarify, in previous videos, I might have referred to forces slightly differently. So I might have written out, say, like G equals mg. So G equals mg, that's fine. That's still the force of gravity. This is just the same idea. It's just expressed slightly differently. So now on this this video, I am probably other videos, I will refer to it as force of gravity. So it's just the force, but you could just say big G and big N for normal force. It doesn't really change anything. Okay, so or T or whatever it might be. All right, so let's go ahead and get into this problem. So the problem reads, a toddler is pushing a 5-kilogram toy shopping cart at a constant velocity across the floor when a pushing force of 14.7 newtons is applied to the right. And it goes through and asks us to do lots of things and solve for lots of ideas. So I'll get into those in a second. But the first thing we're going to start to do is part A here, and that's to figure out the free body diagram, because this is really the most important step. So for part A, we're just going to draw a dot for the shopping cart, and we're going to draw the forces that we believe are acting on this shopping cart. So the dot represents a shopping cart. It doesn't matter. You can always just make the object a dot. Okay. And I'm going to go through and I'm going to underline things, and we're going to label what they mean. So the first number I come to is 5 kilograms. So kilograms is a measure of mass. So that's the mass of the cart. So that's the mass of the object that we care about. Another important phrase that you might see is constant velocity. Another one that you might see in future problems is rest. So we're going to come back to what that means here and think about constant velocity. So if something's moving at a constant velocity, that means that the acceleration is 0. So it's not speeding up, it's not slowing down, it's not changing direction, it's going at a constant velocity. And if your acceleration is 0, what comes out of that is that the net force is also 0, because if you go back to the equation, the net force is equal to the mass times the acceleration. And if the acceleration goes to 0, 0 times anything gets you 0. So the net force is 0. And we talked about if the net force is 0 in previous videos, that if the net force is 0, then that means that the forces are balanced. So all of those forces are canceling out. It's an equilibrium. That's a fancy word for it. But that's the outcome of that type of motion. Like, all the forces have to be balanced out. Okay, 14.7 is another value, and this is the last value that's given. So 14.7 is this pushing force. So I'm just going to label this F push, and I'll say that's 14.7 newtons, and it's going to the right. So if you see newtons, that's what that means. It says it's applied to the right, so that's easy. So I'm going to start with that one, and I'm going to draw it in. So the force of the push. So you just draw your arrow with an appropriate size and the direction of that arrow, which is pointing to the right. Other forces that are happening, if you imagine a toy shopping cart sitting on the floor. The force of gravity is trying to pull down, so that's going to be Fg, or you could label this G, that's fine. There's a force from the floor that is supporting it and holding it up, and that would be the normal force. You could just call that N, depending on which labeling you like. Again, these are balanced, so I'll put these little tick marks to show that, okay, these are equal in size and they're balancing each other out. Because if they weren't balanced, then the shopping cart would either fall through the floor or be like accelerating upward, and that doesn't happen. The last force that we have in here is the force that's going to try to slow things down, which is friction. So again, these are going to be balanced, so you can label it F for force of friction, or you just call it a lowercase f for friction. Either way is fine. It doesn't really make a difference. So that's a good free body diagram. And from this picture, we recognize that all of these forces, the up and down forces or vertical forces, are balancing out, and then the horizontal forces are balancing out. So we've done step one, we've drawn a free body diagram, and now we're going to get into the chart. So this, I don't think is the first time I've shown you these charts, but it's just kind of going through this example. All right, so we have our chart with various boxes, and we have the forces in the X direction and the forces in the Y direction. And if it helps you to kind of draw arrows to represent X and Y, if that helps you, then that's fine. So with X and Y, X is going horizontal and Y is going vertical. I'm just putting a 0 in the middle because that would be like on a number line, that would be 0. Anything to the right would be positive, that's a positive value. Anything to the left would be negative for the X direction. And then for the Y, similarly, 0 is kind of the middle of the number line. If anything above it is considered positive, anything below it is considered negative. So those directions of those arrows tell you what kind of sign the various forces that we labeled in our picture should match up with. This first column is just the forces, so I'm just going to take these forces and put them in here. So you just, from your picture, you're going to write out force push, force gravity, force normal, force friction. It doesn't have to be in that order. It doesn't make a difference which order you put them in. You just need to, everything that has an arrow here should be in this first column. When you add all these up, so if you put all these forces together, you get the total force or the net force. So that's going to be the very bottom. Down here at the bottom, you always get the net force. So this number of forces can vary in the picture depending on how many things you have, but the overall net force is when you add them all together. All right. So now we've set up the table, and now we need to label it with positives, negatives, and zeros. So this step, whoops, went the wrong way. This step is probably one of the most important steps, and it's probably one of the ones that people kind of rush through and don't think through and sometimes make mistakes on. And it's really important because if you mess up a sign, you're not going to get the right answer at the end. So let's kind of talk through this and make sure we understand it. So the first force here is the push, and I just have to look at this arrow. So kind of highlighting this one, drawing it again. I have that force going to the right. So going to the right, that's in the X direction, and it's a positive X direction. So all I'm doing is put a little plus sign in there. Now the second part is the Y direction. So does this arrow for the push go up or down at all? The answer is no, it doesn't. So when it doesn't go up or down, that would be a 0 because we're just at the 0 mark. All right. We're going to do this with the gravity. So I'm going to put some questions embedded in the Edpuzzle here. So for gravity, what's the force in the X going to be? And then the force in the Y, you go ahead and answer that now. And in the X direction, it would be 0 because it doesn't go up or down, and it would be negative in the Y because it's pointing in the downward direction. Similarly, for normal force, I want you to identify the direction of the X and Y components or parts of the force, so do that now. For the normal force in the X, it doesn't go in the X direction, so it's 0. It's going upward, it's pushing up, so that's in the Y direction. Finally, for friction, I'll let you do the friction one now. So figure out the X and Y directions for the friction. And for the friction, it's going to the left, so that's X negative, and Y 0, because it doesn't go up or down. So now we've concluded the drawing and the chart and filling in the positive, negatives, and zeros. So now we're going to figure out numbers. So if a number is given to us, we can put it right in. Notice there isn't any M in this chart, so there's no mass in this chart. We're going to use mass with another idea later on. But we know that the pushing force is 14.7, so I'm going to put that in here. All right, so 14.7 goes in with the force of the push. That's really the only number that's given to me besides the mass. So the other ones I'm going to have to calculate. So for the force of gravity, there's a formula for it, and we said that the force of gravity is equal to mg. So if I plug into that, 5 is mg G is 9.8. And if you put 5 times 9.8 in your calculator, you would get 49 newtons. These are all newtons. All these forces are measured in newtons. I'm not going to write out the units all the time, but you should know that forces are measured in newtons. So gravity is pointing down. That's why we have it negative, and that's going to be 49. The other piece of information that we have is the acceleration. And we already said that the acceleration is 0, right? Because the cart is at a constant velocity. That's why that word is really important, or phrase is really important. So if it's got a constant velocity, the net force is 0. So we can put a 0 there in the bottom in the x because it doesn't accelerate left or right. Also, we said that these two forces in the vertical direction are balanced, so they're not going to accelerate either. There's not a net force in the y direction, so that's going to be 0. So with equilibrium, we get these two boxes to be 0 in the very last row, which is the net force. So that makes it so we are set up to solve for these other two boxes that I'm tracing with a green box to highlight it. So what I need to do is I need to figure out, okay, how big is the friction force? How big is the normal force? So again, if you just add the columns, you say, okay, 14.7 plus some negative number would get me 0. If it's balanced, that means that these numbers are the same. So the friction force has to be 14.7. So if I have 14.7 going to the right, I have negative 14.7 going to the left, and those two forces, they're going to cancel out, and the net force is going to be 0, which is what we want. Similarly, in the x or the y direction, we're going to add the columns there. So we have negative 49 plus some number gets me 0. That's going to be a positive 49, because again, these are balancing out. These up and down forces, if we have 49 down, in order to keep it from accelerating downward, we need to balance it out perfectly and have 49 going up. So those are canceling out, and I get to 0 there. So I've filled in all my information in the chart, and that has actually answered a lot of the questions. So we've done part A, that was the free body diagram. We did that step. Part B asked us to calculate the gravity force. This was part B right here, so we did that. C asked for the normal force. We did that with this idea, so it's 49 newtons for the normal force. D wants us to calculate the force of friction. We did that here in this chart. So again, the chart solves for a lot of ideas, right? The last thing it asks us to solve for is part E, is the coefficient of friction. So the coefficient of friction is that Greek letter mu. It looks like a cursive U. And it's only in one equation. So for part E, we're going to use the friction equation. Force of friction equals mu Fn. All right, so we're going to take the values from our information in the chart and put it in here and solve for mu. So for our force of friction, it is 14.7. And this is where you might say, well, it says negative 14.7 in the chart here, and that is true. For this situation, the direction for the friction is negative. But we're going to solve for this idea of coefficient of friction, and the coefficient of friction is just a description of how slippery the surfaces are, or how rough the surfaces are. And the idea is it doesn't have a preferred direction, so it doesn't always point in the negative x direction. It can point left, right, along the surface in any direction. So I don't worry about the negative when I'm solving for the coefficient. If you do put it in there, I personally wouldn't take it off, but you just want to be careful with that. Finally, for the normal force, we got 49, so I'm going to put 49 on this side, and I need to solve for mu, so I'm going to divide by 49 on both sides. And when I do that, I get something like mu is equal to 0.3. And mu is a unitless quality. So the normal, or the friction force is measured in newtons, the normal force is measured in newtons, they drop out. So it's just a value, it's just a number, it's just a coefficient without any units, it's 0.3. So that is the first problem. This one was a little simpler, and people generally like equilibrium problems because these boxes go to 0. The next one we're going to do, stepping up the difficulty a little bit, it's not going to be 0 in the bottom. It's going to be some values, but you're going to be able to solve it the exact same way using the exact same process. So, so hopefully this is making sense and you're doing well with following along with those instructions. All right, so we're going to go to problem number 2 here. So problem number 2 says a 125 kilogram crate, so we'll label as we go. That's the mass of the crate, is accelerating at 2.4 meters per second squared. So that's A. And as it's being pulled across, sorry, it's blocking there. As it's being pulled across the floor with a rope that has a tension of 375 newtons. So 375, that's going to be our force of tension, or you can just write T for tension. That's fine too. Again, very similar questions. It asks for the free body diagram. B asks for the force of gravity, C as for the normal force. All right, sorry, yeah, C as for normal force. I have two C's. This should be D and this should be E, so I'll fix that here. So D is the force of friction, and then E is the coefficient of friction. Oh, that's not very good, so let me fix that picture. Okay, so it doesn't always have to ask you those things. Like, it might skip a couple steps along the way and say, okay, figure out the gravity, figure out the calculate the coefficient of friction. You would have to do these other steps along the way. So again, we're going to draw our picture. So for part A, our free body diagram. It's a crate. It's accelerating to the right. It's being pulled in the direction that it accelerates. So we're pulling to the right. I'm going to label that the tension. Other forces that are acting: the weight or gravity pulling down, the normal force going up. In this situation, again, they're still balanced. The only time they aren't balanced is if the object is accelerating vertically in some way. So if it's accelerating up or down, then they're not going to be balanced. And then finally, the force of friction is going to oppose it, but it slides to the right and it's not going at a constant velocity. So really, this is kinetic friction, but if you just write FF for force friction, that's fine. So there's your free body diagram. We have the vertical being balanced. The horizontal is not balanced because we have an acceleration. So if we have a value for the acceleration, it is no longer balanced, and it is going to accelerate to the right as described in the problem. Okay, so that's A. So we've done part A. We did our free body diagram. I'm going to set up the table next. Again, this gets very repetitive, so once you kind of get the hang of it and you've practiced it a few times, it's very repetitive. Again, the X direction is going horizontal, the Y direction is going vertical. Again, if this helps you drawing this arrows with positives and negatives and zeros, do that, all right? Because that's what it's there to do. We just label the forces again, so the force of gravity. It doesn't matter the order, the tension, the normal force, the friction. I switched them up a little bit. The net force is always on the bottom when you add them together. Okay. Figuring out the gravity, looking at the gravity force, we're pointing down, so it doesn't go horizontal, so that would be X is 0. For the Y, it is pointing in the negative direction, so that's going to be negative. For the tension, it's going to the right, so that's positive. It doesn't point up or down, so 0 for that one. For the normal force, it's not going left or right, so that's 0, and the positive in the Y because it's pointing in the upward direction, and up is positive. And then for the force of friction, it's going left, or pointing to the left, and the Y direction is 0. So again, all I'm doing is labeling or looking at these forces on that free body diagram and comparing them to the X and Y direction. When I put things together, it says that this box accelerates, it's got a positive value, so that means it's to the right, so this should be a positive number for the net force. And the Y direction, it doesn't accelerate up or down vertically, it just slides across the floor going to the right, so that's a 0 here. Most of the time, it's going to be 0 in the Y direction, unless you have a situation where something's going up and down, or accelerating up or down, like an elevator, or you know, like you're throwing a ball up in the air, or you're throwing a ball downward, something like that. Okay, so we've done the free body diagram step, and now we're going to calculate different forces. So for part B, it asks us to find the force of gravity. So the force of gravity is equal to m times g. So again, we're just using these equations that were given. 125, that was our mass value. 9.8 is the acceleration due to gravity, and if I multiply those together, I get 1,225 newtons. So that's going to be here for my force of gravity. Okay. For the tension, it told me the value, so that was 375. That's what I labeled over here on our original picture. For the normal force, we're trying to solve for this box. There is no formula for the normal force, but we know that when we add these together, they should go to 0. So negative 1,225 plus some number equals 0. So this should be the same value, just in the opposite direction, or 1,225 going up. That doesn't happen in every situation, but in basic ones, that's what happens. So a lot of times the normal force and the gravity force balance each other out. Okay. Finally, in the chart, we need to solve for the force of friction, and we need to solve for the net force. So one of those we're going to have enough information to solve for. The other one is the one that we'll use the chart for, kind of like what we did with the normal force, where we add the things together and get the value. So the thing that we're going to solve for, since we know the acceleration, we can use F net equals ma. So the net force is equal to the mass times the acceleration. The mass is still 125. Our acceleration is 2.4. And if we multiply those together, you get 300. So this is going to be 300 in this box here. And then we just have this friction force is the only thing that's missing. We have to add 375 plus some negative number gets me 300. So again, I have 375 going this way. I don't know what this number is going the opposite way, but I want a total of just 300 going to the right. That's the net. And again, you don't really draw this in the free body diagram, but I'm trying to help you visualize how much this force has to be. So 375 plus some negative number gets me 300, so that's going to be 75. So I've calculated, I did my free body diagram, I've calculated the gravity, I've figured out the normal force, I figured out the friction force. The last step, E, here is to calculate the coefficient of friction. So very similar to what we did in the last problem, we're going to use the friction force is equal to UFN and plug in the values. So 75, if you put the negative, I won't take off for it, but some teachers might, so be careful. The normal force is that 1225 number, and we're going to divide by 1225 on both sides. If you do that math, you should get U is equal to 0.06. Okay, so hopefully those two example problems help you in understanding how to solve these types of problems. It's really coming back to this process, which I like to use. You might do something slightly different, or your teacher might be doing something different, but it's the same basic idea. Like, you start with your picture, based on that picture you fill in your table, then you get into the idea of, okay, what numbers can I figure out from these equations down here? These are the main three that we're using in Physics 111. And then once you have those filled in, you're going to have two boxes in your chart which are missing, and you're going to use the algebra to essentially solve for that, or to try to make the error, like that highlighted box, fill in that highlighted box. And then if you need to, sometimes you'll get the information to solve for the net force with mass and acceleration, or you're asked to solve for the acceleration. And we'll probably do that in other problems in the future. So, all right, that seems like, I think, a good place to stop. So have a great day, and I will see you guys later.